Hi folks, I'm Simmer and I'm excited to walk you through our work, EgoMimic. We're starting to see impressive generalization and manipulation from works like RT1, which collect large datasets of robot teleoperation. But this mode of operation requires specialized hardware and active data collection effort, which poses a scalability bottleneck. In contrast, other domains leverage passively generated data from everyday internet users. So we ask, how can we scale up robot data via passive collection? We present a stack to collect human data for manipulation simply by wearing a pair of Project Aria glasses. Alongside this, we develop a low-cost and capable humanoid which can readily leverage this data. In fact, both our human and robot stack leverage the Project Aria glasses to record data. This approach lets us collect large-scale human data, which closely matches the observations seen by the robot. Our algorithm, EgoMimic, enables seamless co-training on these two data sources. At a high level, our algorithm co-trains on both hand and robot data. We individually normalize the proprioception. We process both via a shared vision encoder and policy network. And finally, output two separate predictions based on the modality. We evaluate EgoMimic on three challenging real-world tasks. In the continuous toy and bowl task, the robot repeatedly picks the toy and places it in the bowl, and then resets itself. This task requires fine alignment with the toy and dexterity to pick and empty the bowl. In the groceries task, the robot must pick a shopping bag via a thin handle and pack all the chips inside. This requires precise alignment to pick the bag and constant replanning because the bag may move throughout the task. Finally, in the laundry task, the robot must fold a polo shirt placed randomly on the table. This requires bimanual coordination since it must use both arms simultaneously. We compare against a number of baselines, including ACT, and demonstrate that our human data from the Aria glasses strongly improves downstream task performance. You can see that ACT often fails to continuously repeat the task, whereas EgoPlay is able to do so many times. We stress test EgoMimic and show that it exhibits real-time replanning. It exhibits robustness to color. And it even shows robustness to robot movement. Further, in the laundry task, we find EgoMimic can generalize to many shirt configurations. Even further, our robot can generalize to entirely new scenes. By combining robot data from one scene and hand data from an entirely new scene, we're actually able to take our robot to this new scene which it has never seen before. And we find that it's still able to complete the task at hand, whereas baselines fail completely. Finally, we analyze our model's scaling properties. We see that as we add more hand data, our policy is able to score consistently higher in the pick and place task. Quantitatively, with robot data alone, performance scales slowly. But by adding 1 hour of human data via EgoMimic, we drastically improve performance. That's all, folks. Thanks for watching.